Alright, so we want to work a practice problem to make sure we're all on the same page and we don't have a hard time using Newton's second law and gravity and weight to solve some problems. So we have the classic bucket problem, where there's a bucket on the end of a rope and you got to lower it down into a well and pick it back up out of the well or whatever. We just want to know how much tension is in the rope for the bucket when it's doing some different motions. And essentially there's only 6 different motions we can have. We can have the bucket at rest. We can have the bucket moving at a constant velocity. We can have the bucket speeding up, moving up. Why would it be speeding up, moving up?
Okay, speed up, move up, that might be me picking up the bucket, right?
Right. So it started at rest, and to get it moving up, you had to, okay. Slow down, moving up.
Slow down, moving up, that means that's like the end of my picking up motion.
Right. Okay, so you raised it, now you're holding it, slow down. Speed up, moving down.
Speed up, moving down might be putting the bucket back down.
And then slow down, moving down.
Slow down, moving down. I'm about to the ground, so I need to
set it down
slow
gently.
it down. Yep.
Right. Okay. Now, there's 6 distinct motions, but I say there's really only 3 cases here. I think we can condense some of these down because there's actually some very similar things that are happening. And if we start with this first one, this at rest, okay, well, if it's at rest, here's my, okay, so here I'm going to have my 6 different scenarios. We're going to see if we can do this, okay? So this is my at rest bucket, okay, or just scenario 1. Let's do it that way.
Okay.
1, 2, 3, 4, 5, and 6. So this is 1, 2, 3, 4, 5, 6. All right. So at rest. If it's at rest, what can you tell me about it?
There's a few things I know of. First, the gravitational force acting down.
Okay,
if you're doing a free body diagram.
Yep, doing a free body diagram for each one of these cases.
Usually how I start everything.
Good
FT
idea.
going up.
FT going up, and since it's at rest, what do you know about these forces?
The acceleration is 0, therefore the forces must be balanced.
Okay, so you say balanced forces, it's at rest, it's not changing, so Newton's second law says net force equals mass times acceleration, and since the acceleration in this case is 0, there's 2 forces, Ft minus Fg equals 0, and so you know Ft equals Fg.
Right.
Okay, so this one, we have 0 acceleration, 0a, and so Ft equals Fg.
Okay, so we can even put a number on it because we know the mass and we know g, right?
Okay, right, remember, so
5 times 9.8 for weight.
5 times 9.8 gets us our weight, and that's 49 newtons.
Cool.
Okay, so we know that the tension force for this one is the weight force, 49 newtons, 49 newtons. All right, so let's go to scenario 2.
Okay, well, scenario 2 actually reminds me of scenario 1 because I have no acceleration again, right?
How do you know that?
Constant velocity means my velocity is not changing, so...
Okay, so Newton's
no
first law
acceleration.
says if something's at rest, it stays at rest. It's in motion, it stays in motion with a constant velocity, unless an unbalanced force acts on it. Since it's constant, the forces are
yeah,
still
we still
balanced.
have balanced forces, so we have the exact same free body diagram, so we'll end up with Ft equals Fg, and there's one where you said we have a similar case.
Those 2 cases are really the same because in both cases, the acceleration equals 0.
So anytime you're at rest or you have a constant velocity, we'll have the weight equals the tension for these.
Yep. All right. So let's go to our third scenario, speeding up, moving up.
Okay, for me, I always draw a free body diagram first. So to speed up and move up, I know I still have Fg acting down.
Okay, so here's Fg.
But I'm speeding up, so I do have acceleration, so I've got an unbalanced force. So I like to draw my arrows showing how big my next force is compared to that one.
Right, that's a good idea.
So speed up, moving up means my tension needs to be greater than my gravity.
Okay, so your Ft arrow, we're going to draw it as bigger, and that actually gives you right there a visual representation. Bigger tension force is going to go in this direction and get faster in that direction. Okay, so this one, and so generally we have to the positive or up be positive. So what we're going to say about this one is its acceleration is positive. Okay, and I didn't give you enough details for anything else,
okay.
So that's
it's
where we're
accelerating up.
Okay, or up. Okay. Let's go to the next one.
Okay, so slow down, moving up. So again, my Fg is still there.
Fg is still here.
But now I'm going to make my Ft appropriately sized. So to slow down, if I'm still moving up, it's going to be kind of the reverse of what we just did. Ft needs to be a little bit less than Fg.
Since it's got to slow down, we need, and it's moving up, but it's
but it's slowing down.
It's slowing down, which means the bottom is actually pulling harder. So our tension force is smaller, which means our net force is actually going to be down, which means our acceleration here is going to be down or negative. So acceleration is negative, or down.
Cool.
Okay. All right. So these two, we can't really group them by
Right.
acceleration.
They're not the same.
They're not the same. Okay. So that means these next two must match these first two somehow.
Okay. So speed up, move down. FG still, we're not changing gravity
FG
ever.
is still FG.
Okay. So speed up, move down. So this is me putting the bucket down. To make it go down, I'm going to have to do a little bit less force than my gravity because it needs to move down.
We want gravity to win,
because
right?
gravity's going to be pulling it down.
Gravity's going to make it get faster going down. So that means my tension force is small again. My acceleration is down again.
Okay.
And so we have negative acceleration. That's down. So that tells us 4 and 5 are the same. Now let's reason our way through on 6 and see if it matches 5 or 3 like we think it should.
All right, slow down, moving down. So this is me just putting the bucket down at the end. So gravity is still the same, but to slow it down, I'm going to have to apply more force than gravity because before gravity was helping me get it down, and now I'm kind of
working against it.
Yeah.
Okay, so our tension force is bigger again, and that gives me a net force up, so my acceleration is up, and so acceleration is positive or up, and so we do see that 3 and 6 are the same. Now what's interesting about this is I look at it in a completely different way. You draw all these free body diagrams, which is nice, it's good, and it shows you everything, and it's the appropriate way when you're solving the problem. But I look at this and I say speed up, move up. Okay, speed up means get faster, so that's positive. In a positive direction, that's positive. Two positives, that gives me a positive acceleration. Slow down, moving up. Slow down is like a negative thing to me. It's getting slower, but it's still moving up, so that's positive. So negative, positive, it's a negative acceleration. Speed up, moving down. Again, speed up is getting faster, positive. Moving down is negative, so plus minus gives me a minus. And then slow down is negative, move down is negative. Two negatives give me a positive, so it accelerates up. So if you want to look at it in terms of how it's moving and what's happening, you can do it that way. If you want to do free body diagrams, do it that way. No matter what, it'll be okay. Now let's actually do one of these with numbers. Maybe well,
probably not the first two cases.
The first two cases, it's 49 newtons.
So let's give it an acceleration, then,
all right? So let's say for one, it's moving up and with a positive acceleration of 2 meters per second, and we want to find tension. Okay, so let me draw the picture real quick. Free body diagram. Here's our 5 kilogram bucket. Here's gravity, Fg, and here's tension, Ft. So it's moving up and it's accelerating up. So it's getting faster moving up at 2 meters per second. Okay, so
per second.
Per second.
So we need
wow, that would be a square. Good call. And so let's see. Newton's second law says.
So I would start some of the forces, and then I would start by saying equals, and then I would look at what forces are acting on my bucket. So I've got Ft going up.
Ft going up.
And Fg going down. So that's going to be plus a negative.
Okay.
Since opposite directions. And that's going to equal mass times acceleration for a Newton's second law portion.
Second law.
So we got some of our forces and then Newton's second law.
So if I have my variables, my mass is 5 kilograms.
No acceleration.
My acceleration is 2 meters per second per second. And
we do know Fg because it's still the same from our previous
G
one.
is
that's not changing.
Meters per second.
We don't change the weight of our object.
Right, we haven't changed that. So really what I'm going to do is I'm going to go through and I'm going to replace this with everything I know. Ft.
That's what we were looking for.
Minus 49, 5 times 9.8 equals 5 times 2, which is Ft minus 49 equals 10. So Ft
49 plus 10.
59 newtons. Now, what's important about this is that you realize this is not the net force. It takes 59 newtons of force to get this bucket to accelerate up at 2 meters per second. The net force is actually right here, right? It's 10 newtons because 5 kilograms are accelerating at 2 meters per second. Mass times acceleration is 10. Okay, but it took 49 newtons just to support it and an extra 10 to make it accelerate up.
So you could even put your numbers on your picture. So like up there you could put your 49.
This is my 49 newtons.
And you can put your 59 on top.
This is my 59.
And just doing what we've done before, if you look at that, you're like, oh, net force is 10.
10 newtons.
Because they're in opposite
directions. So it does check with Newton's second law.
Cool.
Okay. Now, the next scenario, say it's moving up, but it's slowing down. Okay. And so what we want to do is say our acceleration is negative 2 meters per second
All right.
Okay. Other than that, everything is still the same. Mass is still 5 kilograms. The weight is still 49 newtons. Okay. And our acceleration this time is negative 2 meters per second. So my free body diagram, 5 Fg, 49 newtons.
Now this time your Ft is going to be a little bit less,
right.
or we expect it to be less than 49.
We expect it to be less, right? Okay. So Newton's second law, net force equals mass times acceleration. So Ft, it's still positive, plus a negative Fg.
Equals mass times acceleration.
Equals mass times acceleration. So Ft minus 49
equals mass is 5, acceleration is negative 2.
Whoops, negative 2. Okay. So Ft minus 49 equals negative 10. So now when I add my 49 over, I get Ft equals 39 newtons. It's still positive, okay? It's still an upward force, otherwise this would be in free fall, okay? But it's not enough to even balance these forces, so my acceleration is still down, okay? And my net force is negative 10, which follows 5 times negative 2 is negative 10. Okay, so it's almost exactly the same, only in reverse. Okay, and that's why it's important to keep track of sign and what direction things are actually moving.